This is our implementation of the MuZero algorithm, our distributed prioritized experience replay MuZero. So, we first need some background theory about MuZero.
Reinforcement learning is a kind of machine learning, where an agent interacts with an environment over time, seeing what actions lead to what rewards and new states. When it does this, it chooses actions that maximize cumulative reward, and it tries to find out how to play optimally. In reinforcement learning, there's two schools of thought. There's model-free and model-based reinforcement learning. In model-free reinforcement learning, the model learns the policy or value functions directly from experiences and have no explicit understanding of its environment dynamics. This is, for example, Q-learning, DQN, and BPO. While model-based reinforcement learning builds an internal model of state transitions and rewards and uses planning to evaluate prospective actions. It's much more sample efficient and similar to AlphaZero. MuZero is a model-based reinforcement learning agent that learns everything it needs simply by observing raw frames of its environment. Rather than relying on a given simulator, it builds its own compact, latent model of how the world works by using 3 different networks. The representation networks that encode recent frames into this latent state. The dynamics network that predicts the next state based on an action and gives out a reward for the state, and the prediction network that output action probabilities and value estimate from the latent state. The planning happens then in Monte Carlo tree search over latent states, and all experience is stored in the replay buffer for continuous learning.
Which games did we choose for our implementation? Well, as the algorithm is environment agnostic, it can perform well on many different games. We tried it on various games like Flappy Bird, Car Racing, and Lunar Lander. We did not create the games from scratch, but we used OpenAI Gymnasium for the environments. We also utilized reward shaping to help guide the reinforcement learning. Without MDP, the reinforcement learning algorithms can't really learn. And not all environments can promise this. A series of frames have therefore been used to give the reinforcement learning algorithm more states to deal with. With this, it can try to understand physics, like for example in Flappy Bird. Here we have a visualization of how we go from the Flappy Bird environment to an abstract state that the system can actually use. We have a training data generator that uses our environment, our seed networks, and new Monte Carlo tree search to generate training data as episodes that is built up by chunks. These chunks contain real state from environment, the value from the Monte Carlo tree search, the tree policy, the best action to choose from on that state based on the epsilon greedy and the tree policy, and the reward for doing that action. When we run this until the environment either quits, death for example in Flappy Bird, or we stop it. We then insert this into the replay buffer, choose which ones to train from, and then use backpropagation through time to train on this retrieved data. The seed networks then get updated, and we have the bootstrapping mechanism that the training generator uses these newly updated networks. But how is training data generated? One key point in generating data from MuZero is Mu Monte Carlo tree search. What is Monte Carlo tree search? It's a tree search based on Monte Carlo methods. Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling. Monte Carlo tree search, even though initially designed for stochastic games, have been successful for video games with large action spaces. This makes it possible to plan which action trajectories work the best. In MuZero's case, instead of real states, like in AlphaZero, from game environments, we have latent states created from our representation network and dynamics network. There are 4 main steps of the algorithm: selection, expansion, rollout, and backpropagation. Let's try an example with our Flappy Bird game environment. So we start with just a root, but the root node has no children yet, so we're forced to choose it. If it had children, we would use the highest Pukt score to evaluate which node to use. Also adds action priorities to guide the search for the Monte Carlo tree search, so it helps possibly find the best parts of the tree. The next step is the expansion step. Flappy Bird has 2 actions, and therefore expand these as children of the root. The latent states are transformed through the dynamics network using a latent state and an action. We also use the prediction network to get a predicted policy, and we also get a reward from the dynamics network. We then randomly choose one of the children to continue with. We optimize this by doing feed forward on all actions and states in one tensor. The next is the rollout step. We perform a rollout on that latent state L1, and as Google Deepmind said, they only use one in depth. The rollout chooses the best action based on predicted policies and then produces an accumulated reward. This consists of the utility in the end latent state L2 and the reward from doing that the best action to L2. The last step in Monte Carlo tree search is backpropagation. We backpropagate all the information we gathered and increment the visit count of all the nodes we trespassed, just as shown in the image. One important factor in Monte Carlo tree search is exploration and exploitation, and as we use Pukt as our selection score, the amount of visits affect how much the algorithm explores different actions, and since L1 has 1 in visit count, it will choose L2. This shows that we're basically working with a breadth first search initially, but after a while, the search gets guided and chooses the actions that it finds the most valuable. We also implemented Dirichlet noise in the root node to force more exploration, peak noise, only as lasts for the initial exploration and then wears off. Here we have an example of, our Flappy Bird actually running and creating a tree. This is an example of a game with a low branching factor and only 2, so it's a binary search tree. and it has 50 iterations or 50 actions that it can do down in the tree.
During self-play, MuZero records each decision step as a training sample. It takes the real state of the environment at each step and takes from the multi-count research the policy target, that is the visit count distribution of actions, the value target, that is the end step bootstrap return of the game, and action chosen by the multi-count research, or a random action determined by Epsilon Greedy to encourage exploration early on, as well the real reward from the environment. Each time MuZero makes a decision, it stores one such sample in the replay buffer, building a diverse data set of episodes for continual learning. Now that we have the data, we can now train on it using map propagation through time. We form a prioritized mini batch of self-play episodes, and for each decision step, we extract the targets coming from the Monte Carlo research, and the history of the past observation and actions, and the rollout action, the future action to enroll for the dynamics network. The representation network encodes history into a latent state. The dynamics network rolls the latent forward action by action, predicting the next latent and rewards. And the prediction network emits policy and values at each step. We compute the combined policy value and reward loss across an unrolled sequence and backpropagate through time to update all networks. Now we can compute the loss. At each step k, we define the utility return as the utility of the real rewards discounted with the real utility from the multi-count research, and then we can compute the per step loss for using mean square error for reward and utility head, and cross entropy loss for the policy head. In addition, we also add weight decay to make the entire network distribute the activations and make it use all of its network, and propagate it through all of the networks.
Here's a simplified network architecture of all of our networks in our project. For example, here you have the representation net, the prediction net, and the dynamics net, and how they work together, and how we get the reward from them, and all of the building blocks inside them. Very simplified.
So these are actual network architectures. As you see here, they're quite large, quite complex, using residual blocks with skip connections and correlation layers and pooling layers. We have created a configuration system that makes it easy to change the different networks. We also implemented distributed prioritized experience replay, as we experienced that this MuZero was extremely sample hungry and sample inefficient. So we needed it to prioritize the experience of the replays to make the model converge faster at a higher level. So we sample the episodes to train on using the temporal differencing error. So surprising experiences get replayed more often, and that is especially good for sparse reward environments. Using distributed prioritized experience replay, we have multiple actors generating trajectories concurrently, reducing the buffer staleness and letting us have more data, and we have a global replay buffer and a parameter server that allows both learners and actors to work together. Here are our results. As you can see, all of the losses go down quite quickly in the start, and with time flattens out and converges. We have sometimes experienced that the loss goes up over time and then goes down afterwards. You can also see here how the learning rate is changing throughout the time, and we use cosine annealing learning rate scheduler, and for the reward you see that it goes up and converges quite early. Here you can see our best agent in action for car racing. As you can see, it can drive and navigate the road. However, this was our best agent, but after a few video matches afterwards, it forgot this useful behavior and become worse. Based on all of our experiments, we can see that the model actually learns. It becomes better over time. However, it converges quite early and often suboptimal minima. It has a particularly hard time with sparse reward environments, and it's extremely sample inefficient. It takes long training times and even days to do experiments. And after time, it does not explore more. So it gets stuck in its local minima. And good agents tends to have a policy collapse after a certain amount of time. If we make the model do more exploration and do more compute, maybe we can make it even better.